Structural Analysis 3 Direct Stiffness Method. Develop the stiffness matrix of the continuous beam by the direct stiffness method and calculate the support moments. So in this case, we are considering a continuous beam. Here the beam is overhanging, so in order to convert it into an equivalent structure with a simply supported, we should convert the end forces into the moment in this way, that is MBA, MBA, MBA. This is BA, MBA equal to 100 into 3 since it is in the anti-clockwise direction. This is in the anti-clockwise direction. A minus sign is provided, so minus 100 into 3 is minus 300 kilonewton meter, and MDE, MDE, and this is in the clockwise direction. So the moment here is 100 into 200 kilonewton meter. The equivalent structure is drawn by showing the moments. The next step is the formation of or finding the degree of kinematic indeterminacy. We know the equation 3j minus r plus m, and the number of joints here. How much joints are there? There are 1, 2, 1, 2 and 3. 3 joints are there. So the number of joints 3. Number of reactions. Since this is a fixed joint, this is a roller and this one is also roller. We have here 2, here 1 reaction and here 1 reaction, and a total of 4 number of reactions. Number of members will be 1 and 2. Number of members is 2. So the degree of kinematic indeterminacy is 3. Okay. So the rotation at B, C and D, at B, C and D, theta B, theta C and theta D are the 3 independent displacement components. K will be in the order 3 into 3 since we have 3 degree of kinematic indeterminacy. After that, we have to draw the global or system coordinates. This is how it will look like. After drawing the global or system coordinates, the next step is to draw the local or element coordinates. For the beam B, C and D, mark the coordinates in the clockwise direction. That is for BC 1 star, 2 star, and for CD 1 star, 2 star. After drawing the local or element coordinates, the next step is to find the displacement transformation matrix. For the member BC, what will be the displacement transformation matrix? Consider the member BC. We have the effect of 1 and 2 coordinates. Consider due to the effect of this coordinate 1, it will have the effect on 1 star since it is the nearest one, and it will not have the effect on 2 star, and vice versa in case of the coordinate 2. That's what written here. So due to the effect of coordinate 1, the effect on the 1 star will be 1 and on 2 star will be 0, and while considering the coordinate 2, the effect on 1 star will be 0 since it is far, and 2 star will be 1. Similarly, we can find the displacement transformation matrix of the member CD. The next step is to find the element stiffness matrix. The stiffness matrix of member B, C and CD with reference to their respective element coordinates are. So in order to find element stiffness matrix, we have the formula 2EI by L into matrix 2, 1, 1, 2. Here the I is for BC is 2I and in case of CD it is I. Substitute the proper values for the members and find the element stiffness matrices. Next step is to find the stiffness matrix for the member structures. We have said in the previous video that the formula to find stiffness matrix for the member structure is matrix KBC equal to DBC transpose KBC into DBC. Substituting the values, we'll get the stiffness matrices for member structures for the members BC and for the members CD. Next, we have to find the modified stiffness matrices for member structures. The above matrices, that is KBC and KCD, are not immediately subjected to superposition since the column in the three matrices are under the different influence of delta. To make them compactable for addition, expand each of them to the order 3 into 3 by adding a column and a row of zeros for the nodal displacement, which is irrelevant for the corresponding members. So we have to find the modified stiffness matrix for the member BC. Since for BC it have the effect of delta 1 and delta 2 and the delta 3 value is absent, we have to provide a row and a column of zeros and form a 3 into 3 matrix. This step is same in case of member CD. In member CD, it have the effect of coordinate 2 and 3, but it doesn't have the effect of delta 1. So in that position, we have to provide a row and a column of zeros in order to form 3 into 3 matrix. After that, the next step is to find the total stiffness matrix. This is easy since we have to add the values KBC and KCD to form the total stiffness matrix. Adding up these values, we'll get the total stiffness matrix. Thus, the matrix can be developed. Thank you.